It's a great pleasure for all of us to be here at COP30, even though we are not in Belém. But it's great in these dialogues to have this panel on digital technology as a driver of the climate and sustainability transition. Speaking of sustainability, the UN has given to the world the 17 Sustainable Development Goals, and none of them can be solved without digital technology, without computing technology, without artificial intelligence technology. All of them seen as a group. And the issue with, like everything else in life, whenever there is something good, there is also something potentially negative. As I said, none of the 17 SDGs can be solved without our technologies. If we look at the 169, or now it's a little bit more, the targets that we have, 70% of them depend on digital technology. And this 70% of the target is spread around the 17 Sustainable Development Goals, including climate, of course, which is at the center of our attention in this panel because of COP30. And the same thing is about data, because data is very important. And some of the panelists will talk about data. The indicators that we have, most of them require lots of data, and the data is not always there. So our technology is at the center of achieving the Sustainable Development Goals, including SDG 13, climate action. And the relationship between the sustainable transition and the climate transition and digital technologies is not just on how these technologies can be used to solve, but also these technologies create issues, bring the effort for sustainability and for the climate action push in the other direction, because our technologies are very energivore. They consume a lot of energy. It's not, and usually it's not energy produced in green ways. So how can we employ these technologies without having all the good, but minimizing the negative implications? These are the main themes that we'll discuss in this panel, and it's a great pleasure for me to have this great panelists. So they will give us a first position for a few minutes, up to 7-8 minutes now, and then I'll ask some particular questions to some of them, one question to one, another question to another, and then in the end we'll have questions that possibly will come from the room. I don't have any image of the room. I don't know how many people are there and how they will be asking questions, but there's so much material that I don't think we'll have trouble covering the time. So without any further ado, let me ask for Professor Virginia Dignum to start the panel. Professor at the University of Umeå in Sweden, and leader of the Responsible AI Lab, and co-chair of the ACM, Association for Computing Machinery Technology Policy Council. Virginia, the floor is yours, about 8 minutes.
Thank you very much. Thank you for inviting me to be here. It's my pleasure to be part of this panel, and I look forward to the discussions. I would like to follow up on what you just introduced, and indeed stress the issue that technology, and especially digital technology, is in relation to climate and to sustainable transitions. We can see it not even as a double-edged sword, but a multi-edged sword. Yes, we can look at AI and the digital technology as an enabler for decarbonization, but that will only work if we really look at AI with a perspective of a systemic design. Already there is lots of AI used for instance, supporting reliability of grids, for weather forecasting, for agriculture optimization, and so on. But those benefits can only really materialize when we design the systems to avoid the rebound effects and to be aligned with the safe and just planetary and societal boundaries. At the same time, or because of that, we need to look at developing technology aligning with this, what I would call planetary stability. The current deployment and development of AI is embedded in the same socioeconomic systems that are at the same time driving planetary destabilization. So looking only at efficiencies and gaining efficiencies through technology is not enough. We really need to look at it from a much broader perspective. We need to look at it, like I say, from this perspective of planetary stability, not just by minimizing the footprint of AI and the digital technology, but really to steering the impacts of AI towards sustainability goals and towards societal benefit. This means that we need to look beyond energy, beyond the use of resources, to the systemic consequences of these systems, the rebound effects, the accelerated consumption, or the concentration of power, which are issues that we are all at this moment really seeing mostly the malefic effects of these issues. So sustainable computing is a life science requirement, is not something which is just about the products, the software and AI products that we are developing. Efficiency improvements need to be matched with absolute emission reductions, for sure, but at the same time, we need to look at alternatives to this type of, to the development life cycle of this. It's not just continuing this chase for bigger data, for more data, for bigger data centers, for more hardware requirements and so on, but to really investing on alternatives which are modular, which are distributed infrastructures, and all what understanding what can be done for the responsible scaling of these systems, which is definitely different from the growth in terms of the size, looking at size alone and quantity alone. So governance, to achieve that, we really need to look at sustainability as a collective action challenge, and using and this collective action is supported by equal access to AI. If we have an unequal access to AI, we really are exacerbating the inequalities, and it will slow, at the end of the day, the global progress. So we need to have equitable access to tools, to data, to infrastructure, looking, like I say, from a distributed and modular and scalable perspective, rather than from a growth and undiscriminated growth perspective. And especially we need to take into account, much more into account, the requirements, the capabilities, and the possibilities of the global majority and those actors with resource limited. We probably need to look much more at how to address open data, open models, transparent methodologies, and all other alternatives to enhancing the global capacity and with scientific integrity. At the end of the day, AI that erodes trust, that really diminishes our capability to trust and to cooperate, AI that amplifies misinformation or that polarizes societies, is an undermining for the long-term decision-making that we need, and collective decision-making that we need for climate action. So we really need to look at strongly aligned systems that reinforce democratic resilience, that reinforce the access and the capabilities for all to participate, to look at how to do this from a a perspective grounded in scientific evidence, and therefore we can then look at systems that are aligned with planetary stability, and at the same time really support also public trust. I think I leave it here, and then we can discuss it further in the Q&A.
Sounds good. Thank you very much, Virginia, for setting the stage with the issues that we have in our hands are holistic and are not just one-dimensional, like energy or anything like this. So we'll continue. Well, let me continue in this direction. Andrew, professor of computing at the University of Chicago, and the other side of the Atlantic. Thank you very much for being with us, especially given that it's 6 a.m. If you are in Chicago, it is 6 a.m. So we see your slides, but not in presentation mode. I don't know if you can, yeah.
Let me see. So thank you for having me. It's great to be here. Oh, it's going into some. How's that?
Yes, now it is perfect. Thank you.
It is breakfast time over here, so I'm just up, and winter just arrived. So here in Chicago, it's we had our first snowfall over the weekend. Thank you for inviting me, Giannis. It's a pleasure to be here at COP. I'm just going to say a few words. As you may know, I work in the large-scale computing space, a lot of work in data centers and grids recently, so I'm going to kind of bring that perspective. So I'm going to talk about how AI's growth can help the world decarbonize or help with energy transition. So I think you've probably all seen the various projections that have been put out. This projection is from the Lawrence Berkeley National Lab, and it's the projected consumption of electricity in the United States from, well, 2024 when the report was put out through 2028. And of course, it's pretty concerning how rapid the growth is. The authors of the report told me that they didn't project beyond 2028, one, because of the great uncertainty, but two, because the numbers were getting so large that frankly, it was a little bit scary. So this growth is of course causing lots of challenges in the engineering of the grid side of the house. So the data center power demands are actually bumping up against our capacity, right, to actually deploy new load. And also actually harming grid stability due to their high frequency behavior. At the same time, we have leading executives and leaders from large data center companies saying, we want to grow, but we can't get the power we need. So there's this fundamental economic and commercial tension already. Now, it's not just, in this kind of study, national study. This is data from the PJM forecast for the Dominion region, better known as Data Center Alley. And what you can see in this space is they've gone through a very rapid change from relatively flat projections in 2021. Let me see if I have the build here, to much more rapid growth projections, that have gone in that region up to 14 gigawatts increase for the 2030 window. So a plus 73% increase in just a few years. Now, the reason I show this slide is not just because it shows how dramatic the increase has been, but to point out that in this Dominion region, the expectation is the data centers will be as much as 50% of grid load by the 2030s. Now, I don't expect it's going to be 50% every place, but it gives you some sense that in some parts of the world, it is a very extreme kind of situation. In Ireland, it's, I believe, over 20% now, and there are many other regions of the world that are in the teens. What I like to remind people is that often journalists and the general media like to point at this and say, oh, this is a huge AI power demand. And that's the popular way to talk about it. But in fact, this demand has been growing rapidly because of our base technologies in computing or digital technologies for, perhaps since the late 2010s, right? So this is a plot that came from a Goldman Sachs study. We have done similar scientific work that shows, in fact, the cloud had turned the corner and begun increasing very, very rapidly in its power consumption as early as 2018. And as you can see from this picture, their presupposition is that the vast majority of the increase you might think of as traditional cloud demand, not necessarily GPUs, right? Which is what we think of as AI. Now, it's probably not productive to try and separate these two things too carefully, because computing and AI are increasingly synonymous, and AI in various forms is being wrapped inside of computing in nearly every aspect. But I just wanted to make the point that this is not a new and uniquely AI problem or AI challenge. It's actually largely a computing challenge that arises from changes in the fundamental technology scaling that we've seen, such as the end of Dennard scaling, the end of Moore's law, and manifested in higher and higher power CPUs, and of course, extremely high power GPUs as the building blocks of our computing. So that, in my part of the world is really, how we frame the problem. There's one more aspect of this that is a little bit surprising to some people. So one of the things that's happened with these very, very large computing loads is that they're dynamical problems for the power grid. So this graph at the left is training dynamics running stochastic gradient descent in a bunch of parallel, iterative, model parallel kinds of training runs. The power can fluctuate dramatically, like many, many megawatts from top to bottom. So that's one problem of these so-called 100 megawatt or gigawatt data centers you see out there. If they fluctuate like this, it causes the grid dynamic control problems. The second thing that can happen, and this happened in Texas, is that you can see that the instantaneous load in Texas dropped dramatically. This is, I think, several gigawatts in just a few minutes in 2024. And the reason that this happened was because the data center behaved exactly as it was designed to do. There was a ripple in the power supply to the data center. The data center detected that and decided the grid was going down. It flipped over and turned on all of its backup generation and took itself off the grid. Right. That was great for the data center. The data center was reliable. It computed right through this. But the grid saw a massive drop in load in just a very, very short period of time. So now we have the problem that data center load has become so large that it needs to be a better citizen on the grid. It needs to not produce these kinds of high frequency harmonics, and it needs to not abruptly jump on or off the grid, right? So we all know, right, that there's been a very significant backlash against this growth of data centers, and computing, once the darling, right, of industries and the most attractive and clean industry and wonderful thing that we all admired, is now actually, losing a bit of its luster, and particularly in this data center area, we're seeing a huge backlash against additional growth and so on. So I think, one of the challenges is technical. Another of the challenges is community, social, and public policy, if computing and AI is going to advance in the technical sense. But coming to energy transition and this question of what does AI have to do with sustainability, or what does computing have to do with sustainability, what is our responsibility? I'd like to remind people that computing's role, of course, is not only negative, right? It's actually positive, and we have a choice for how to shape it. We could go on and on about the brilliant applications of computing to address sustainability problems. As Giannis has pointed out, computing and digital technology is fundamental to our ability to understand, model, and intervene. But let me just focus a little bit more narrowly in this area of data center growth. Yes, of course, we need to ensure that data center growth is sustainable as possible. And that means regulation, incentives, standards, and oversight. But I'd like to point out that this rapid growth, probably the largest capital investment we've seen in our lifetimes, right? Hundreds of billions of dollars seem to be pouring into this space every day. People talk about many trillions of dollars being invested over the next 5 years. And of course, we all know in energy transition and sustainability, the biggest challenge we've faced in many ways is creating the scale of investment necessary to drive energy transition. So I view this not just as a challenge, but also as a huge opportunity. So what are some of the opportunities? First, the rapid growth of power generation and grid infrastructure, which is coming from this increased load, is a huge opportunity to transform our grids for the energy transition. I mean this with no disrespect, that most power grids around the world are built on what I would call dumb 1950s technologies and 1970s economic structures and markets. They frankly don't reflect the reality of distributed generation, rapidly fluctuating loads and volatile renewable generation, and of course, markets designed for large-scale uncertainty that comes from all those generations. So there's an opportunity to rebuild our power grids with all of this investment, to be dynamic and flexible, exploiting, of course, extremely fast digital control that is possible over ranges and distances and scopes because of fiber optic and wireless communication. The grids can be, instead of unidirectional, from big power plants down to the edge, bidirectional with distributed generation. And of course, they should have markets that are better designed for volatility, right? Our markets are just teetering on the edge, barely coping with the rapid fluctuations we have in power generation and load these days. So there's the opportunity not only to have a better infrastructure, but to speed decarbonization and increase reliability. So that's one big opportunity. The second big challenge for the energy transition is how to mate what data center loads look like, which is basically this boring kind of flat line, with this kind of complex generation mix that you can see. This is taken from the California power grid, and you can see the purple area is the wind generation fluctuating, and the yellow area is the solar generation fluctuating over days of a 4-day period. And then of course the load itself is fluctuating, you can see at the top. So the grid has to perform this balancing act and do this all the time. And this is getting more and more challenging because the fluctuation is getting greater and greater as the renewables are a larger fraction. So one major opportunity that's emerged is this idea that data centers can be dynamic loads. So this is the second opportunity. So if data centers are going to be 10% of the power grid load, and frankly, you know, we don't believe that it stops at 10%, right? It could well be significantly more than that. It's a fast-moving and controllable load. They're owned by sophisticated, wealthy operators. I don't mean that every data center company is as rich as one of the, you know, what we call in the United States hyperscaler, you know, cloud companies. But of course, you know, data centers in general are a high margin advanced technology space. And of course, these loads are highly networked, of course, right? Fundamentally, they're computing infrastructure things. So this data center load flexibility can enable more reliable, efficient grids. It can provide visibility into load planning, which is critical for this balancing. And this flexibility can accelerate grid decarbonization and the capacity at the same time, decarbonization and the increased capacity in the grid that these data center companies dearly want. And the flexibility can reduce the massive energy storage that we're looking at as being necessary, needed to create reliability from wind and solar alone. And this is a huge impediment to decarbonization. Okay, so I should try and finish up probably.
Andrew, yes, can you please, yes.
Let me show, we have some technology ideas for how this can be done to allow people to do this. But let me just say, the last idea for opportunities is much better grid control. So the old grid depended on loads and generation moving slowly over hours and was highly predictable. The grid can have rapidly with milliseconds, seconds, and minute timescales, flash events, all kind of stuff. So you have rapidly changing loads, you also have rapidly changing generation and lots of small controllable assets. So this is a huge opportunity to adapt and control this more complex grid with modern controls, high-speed nonlinear dynamic control, enabling all kinds of dynamic response and reliability. And the net benefit of this is not only reliability and lower cost, but more aggressive decarbonization. So with that, let me finish up. Thank you, Giannis. Thank you.
Yeah, thank you. You really gave us a great picture of the energy part, which is not the only one, but certainly a very central one on how we achieve sustainability and certainly the climate transition. And it shows that there's a lot of work to be done at the technology level and so on. Now let me move forward to Jayant. Jayant is a professor of the Indian Institute of Science in Bengaluru, Division of Electrical, Electronics and Computer Sciences. Jayant, what do you have to say about what we are facing? Data probably, partly, but what else?
Yeah, so firstly, thanks, Giannis, for the invitation to this panel, and greetings to the worldwide audience. At the outset, I should confess that I'm at somewhat of a disadvantage compared to the other panelists because they have actually done research on sustainable climate action, whereas my engagement has been more of an observer and a consumer of these activities. But so what I'll do is to just talk you through some of the activities that I've seen that have happened in India over the past decade or so. And since India hosts about 1/6 of the world's population, our actions on climate actually affect not just a large part of humanity within the country, but also all the neighboring parts of the world. My view of the digital technology is that usually it's viewed as digital technology feeds into AI, but actually I see this as a pipeline that digital technology is initially responsible for giving you the data to observe. And then there is AI, which does the interpretation of the data. And then you again have digital technology implementing the actions recommended by the AI. So in that sense, there's a virtuous cycle between digital and AI that would hopefully result in good sustainable computing. So with regard to data collection itself, you might have heard that we have an Indian space research organization which has been extremely successful, especially in recent times. 2 years back, we had a moon landing, and this was also on the far side of the moon. So we have a large number of Earth observation satellites, high resolution remote sensing, large network of Doppler weather radars, and then we collect a lot of information about rainfall, sea temperature, glacial melt, and so on. And I know that you would all be probably aware that the monsoon is central to the Indian economy in all aspects. So there is a huge amount of modeling work that happens with regard to forecasting and real-time climate dashboards and so on. So what has changed in the recent years is that earlier these were largely computational models where you fed the data and then there was some mathematical model that went into it and produced some answers, and the predictions were not particularly good. But today these systems are now enhanced by AI and machine learning. So the risks are being modeled with much greater precision. So we are using AI tools to predict crop losses from heat waves, map those areas which are vulnerable to floods, or assess coastal erosion, which is critical in India because we have a very long coastline, simulate the long-term impacts of climate change on biodiversity, water resources, and so on. So this is the science-backed and combined with data-driven approach is allowing us to design stronger climate adaptation policies. Specifically with regard to agriculture, which is again central because we have such a large population, we are using, even our farmers today are using soil moisture sensors, drones, and even mobile-based weather apps. And these give you hyper-local forecasts because at earlier, most of the forecasts would be over large regions. And we know that the microclimates are much more important to agriculture than getting a big picture here because things change a lot even in small areas. So we have platforms for a variety of government as well as non-governmental organization platforms, which give this climate smart advisories. And this is directly done to the farmers' phones. So one of the things that has happened thanks to digital technology is that there has been revolution in India with regard to communication. Everybody has a cell phone. In the sense that that has primarily become the mechanism by which everybody communicates, does their finances, does their banking. So the phone has completely revolutionized the way that people lead their lives. In fact, even if you go on the metro trains nowadays, nobody's looking at each other. Everybody's looking at their phone. Okay, so it's to that extent. So we find that these tools actually are very useful because it's individual specific and they help to minimize the risks because we have had completely unpredictable monsoons, especially in India and Pakistan. In recent times, we have had both droughts and floods at the same time, as well as heat waves. So for all of this, the digital technology has become very important. Then already Andy talked about energy, which is one of the largest contributors to emissions. So we have tried including smart meters, smart grids, and remote monitoring systems. There is also a rapidly expanding solar and wind capacity. And because the country is large, there are various regions where you can have solar. For example, we have Rajasthan, which is almost completely a desert. So there's a huge amount of solar energy that can be tapped in. There is a national electrical grid that combines all of them together. There's also a lot of wind capacity. And the digital technology helps in ensuring that there is a flexible and seamless coordination of all these grid management systems. Then coming to transport, which is one of the most contributing to urban emissions, we have been having a similar transformation. Just as a simple example, earlier, whenever we used to go on highways, there used to be toll booths and you had to actually physically pay the money to them, which meant that there used to be long lines of cars and trucks waiting for this payment, and there used to be a large amount of emissions in those regions. But now we have a lot of what are called as fast tag devices, where basically the car gets scanned and you automatically pay the toll, and you don't have to wait for a long time and basically utilize fuel while you are still idling at the toll booth. And then there are also intelligent traffic management systems for traffic lights and ensuring that you don't get into congested areas and stuff like this. What has perhaps been one of the most remarkable things that have happened in India is the payment mechanism. So although payments doesn't directly seem related to climate, the point is that now we can do everything through mobile phones, including paying street vendors for sandwiches. And because of this, there is almost no paper money being used, which means that you are cutting down fewer trees in order to produce the currency bills and stuff like this. So thanks to this, what is called as the UPI or United Payments Interface, it's a real-time instant payment system, and that basically connects the mobile phone to the bank. And therefore, essentially, you have the bank in your phone. And you can pay for anything, even the smallest vendors now accept these payments. So almost all paper money has completely gone out of the economic system. Uh, but what I would say is most important, apart from all of this, is that you need to have citizen engagement. So we have several apps produced by the government as well as other agencies that allow citizens to report pollution or to track waste management or to participate in climate campaigns. And I think one of the things that, of course, Yanis would be very happy about is that ACM India, which is the regional council of ACM, has been playing a role of an enabler and multiplier in this respect. For example, we have had a summer school on climate, which was in a few months back, and this was on AI for social good, and it featured talks like building solutions using AI, agriculture, and climate. Then we also had a summer school on data science, where it had hands-on data-driven modeling for earth and climate sciences. We have an eminent speaker program, very similar to the distinguished speaker program that ACM has. And again, there has been a lot of interest from the students on climate technology. A recent talk was using climate-focused technologies for tracking and improving air quality. We have also had chapter summits. And actually this year, the summit theme was sustainable computing. And so you can see that sustainable computing has essentially become center stage for us. But what I would suggest related to what Virginia was talking about earlier about democratization is that we can talk a lot about what are the disadvantages of the kind of climate changes that we have seen, but that is not going to have much effect, because when people are finding it difficult to find where the next meal comes from, nobody is bothered about climate. So we really need an incentive mechanism to encourage people to make sure that they make climate aware kinds of solutions. And just to give you a kind of a frivolous example, all of you have attended many of the ACM conferences, and you'll find that most of the times on the very last day, which is usually a Friday, half the participants have left because they want to get back home, and you find that in the last 1 or 2 sessions, there's a very small audience. But in VLDB 2003, which was in Berlin, they did a very interesting exercise. They said that there would be a lottery in the very last session where anybody who was present and their registration ID was called out, they would get automatically a free registration, which is a large amount, about $800 or so, for the next VLDB conference. And we found that you had a complete audience because everybody felt that they would win the lottery, and it ensured that there was 100% attendance even on the last day. So I think especially in developing countries and poorer countries, you cannot try to appeal to people's worries about what might happen with climate, because that's too far in the future. Instead, you need to talk to them about how to incentivize it. And a recent example that happened in Mumbai, and Yanis would know this well, because in India, there's a lot of honking when you drive, okay, because it's kind of becomes second nature. And that's the way that you actually move forward. In Mumbai, what they did is at every traffic light, they said that the more you honk, the red light will go on for a longer time. So it was a disincentive that you should honk, because then you will have to even wait even longer. So then people started quieting down. Okay? So I'm saying that we need to use game theoretic principles to get people to actually participate in climate and not threaten them, but actually encourage them to participate in this process. Okay? So that's a quick overview of what's happening in this part of the world.
Thank you. Thank you, Jayan. So digital technology is one thing, but human technologies
Yes,
and
well,
human
yes.
behavioral technologies and tricks are there to stay. And you said that all of us have been to ACM conferences. Phoebe Kunduri has not, and it's about time that we bring her to one of them. She has been in ACM activities, but not to an ACM conference yet. Phoebe Kunduri, a professor of economics, especially environmental economics, at the Athens University of Economics and Business. And she has so many titles, I won't go through all of them, but very central in the United Nations Sustainable Development Solutions Network, the Global Climate Hub, sustainability in the Athena Research Center, and so on. So you heard from essentially computer scientist Phoebe, put us on the right track. You have again about 8 minutes. You can share your screen. I think you are presenter as far as I understand.
Okay, for some reason I cannot, but it's okay. It's not a big issue. So 3 months ago, I've been given the responsibility by the General Secretary of the UN to lead, to be the chief scientist for the Global Sustainable Development Report. This is a report that the UN publishes every 4 years, and it's basically an assessment of assessments with regards to the implementation of Agenda 2030. Agenda 2030 includes the 17 Sustainable Development Goals and the 169 targets within these goals. And the idea is that this agenda gives us a holistic, integrated, science-based framework in order to transpose ourselves, in order to move away from the current multi-crisis to a sustainable development path. And not only the agenda exists, but in 2015, it was signed by 193 countries. And this is the biggest number of countries that have ever signed a global agenda of the UN. The Charter of Human Rights, when it was launched, it was signed by less countries. So there is political endorsement of these SDGs. I can also tell you, as somebody who has been working a lot on this space, that this is a brilliant science-based framework that can allow us to escape our current situation that features economic problems, mostly relevant to 1/3 of the countries of the world being at the brink of default or being at default. Fiscal spaces across the world, including global north and of course global south, are shrinking. We face inflationary pressures. And in addition to this economic crisis, we also face existential planetary crisis, including, of course, climate change, biodiversity collapse, energy insecurity, food insecurity. And in addition to all this, and because of the above, the economic and planetary crisis, we are facing problems with social cohesion, increasing inequalities, and all of this leading to geopolitical pressures. We know that the multilateral system is facing difficulties. The UN system is facing difficulties at the moment that we speak. So this agenda, the holistic integrated agenda, that of course includes climate as one of the SDGs, SDG 13. And of course, climate is one of those SDGs that touches upon each one of all the other 16. The good news about this agenda is that we have the science, we have the technology, we even have the financial resources in the public and private space to implement it. We do have this. However, implementation is at the level of about 20%. We have developed elaborated metrics frameworks that allow us to measure the level of implementation at different scales: global, regional, national, subnational, local, even at institutional level and at company level. We can measure the performance against the SDGs. So we know that on average, globally, the performance is 20%. We know that we have 5 years left. And the aim of this report that I'm leading is how we can accelerate the implementation by the 2030 deadline, but also, and importantly, define the future beyond 2030. I'm going to give you quick answers to these two. The first quick answer is that for acceleration of implementation, we need accountability and an explicit implementation mechanisms that will streamline all the science, all the technology, all the financial resources and capacity building to achieve scalable results on the ground. It can be done because, as I said before, we already have the technology, the science, the technology, the fiscal and financial resources. Now, specifically on climate, we work with Professor Ioannidis, my good friend Yannis, on developing a global commons for enabling the countries across the world, all the UN countries, under the auspices of UN Sustainable Development Solutions Network, to design these needed detailed pathways for each and every country to achieve SDG 13, which is the SDG on climate action. And what we do there, yes, we start from measuring where we are. We also make explicit where we want to go according to the goals, to the definition of the goals and the targets within the goal, but also according to the explicit policy frameworks that have been developed in each different country that try to mobilize and accelerate the design and implementation of climate mitigation and climate adaptation policies. And to design these pathways between where we are and where we want to go, we have developed an elaborate machinery, let's say. Machinery in terms of technology, not technology only in terms of hardware. I'm not referring to hardware. I'm referring to a structure, a method, and the documentation of this method on an open access AI-ready platform that collects all the data that we need for our mathematical modeling. And the mathematical modeling is elaborate and integrated because it's not enough to just include the climate modeling and the downscaling of this modeling to different geographical scales. You also need to integrate the climate projections with your modeling of the transition, dynamic and spatial transition of the energy system, the transport system, the land use system, including food systems and forestry, the marine use system, the technological and innovation system, and then embed the integrated dynamic and spatial solutions for these systems that will allow them to detail the changes that need to take place in order to move from where we are today to the full implementation of the goals by 2030. And then embed these detailed transformational changes. And let me make these changes explicit. These are technological changes, policy changes, governance changes. Embed these changes into the socioeconomic system, which means embed these in general equilibrium socioeconomic analysis. In order to answer two questions, where is the finance coming from in order to finance the implementation of the suggested optimal mixture of changes that will lead you to net zero and climate adaptation? And then how do you protect the vulnerable in this transition? While collecting all the data and making it available, our models, making the models available, when we are solving this integrated modeling system, we introduce the stakeholders. The stakeholders are very important. The stakeholders are there every step of the way in order to validate, correct, add, subtract their own knowledge, vision, fears, preferences in the coefficients and even the structure of this modeling exercise. So we make the stakeholders shareholders, owners and shareholders of the design pathways. And to be true to them, we also offer them education, upskilling, reskilling, in order to truly understand in each country the issues on the table. We have a hub, an SDSN hub in each and every country of the world where we gather representative stakeholders that are there to co-design the transition pathways to climate neutrality. At the end of the day, what you
can
have...
wrap up, yeah.
I am wrapping up now. At
Good.
the end of
Wonderful.
the day, you have a set of tools, visualization dashboards, decision support systems, and digital twins that have three main layers: the natural resource layer, the technological engineering layer, and the socioeconomic layer of the transition pathways to climate neutrality and climate resilience. And we think this is important because traveling in more than 120 countries across the globe and talking to stakeholders on what they need to really engage with the climate transition, with the climate mitigation and adaptation transition, the answer was explicit guidance, detailed pathways that they can implement, they can scale, and they can finance. Thank you.
Thank you very much, Phoebe, for bringing us on the trenches of what is happening at the UN, SDSN, and across the globe. Let me ask a few questions now, trying to connect some of you. And of course, as you are giving very short answers, because we have, even if we go a little bit overboard, we have at most 10 minutes. So very short answers. Virginia, you talked about This is not only about energy, it is holistic, it is democratization. Phoebe just presented a systematic, if you want, thinking and approach that involves everyone, all countries, all layers of nature, money, and tech. The way we are proceeding, does it satisfy what you are envisioning, or saying it's mandatory, or do we need more, or what do you say?
I think that we need more. I liked what Giant says in terms of creating the real incentives that make people move, which are not necessarily the long-term benefits for all of us. Unfortunately, that's reality. I also think that still we are too much expecting a development of the digital technologies along the lines in which they are going. And thank you, Andrew, for explaining how the complexities of the data centers and the energy capabilities are. I do think that, at least personally, and many others think about that, we do need to take a completely different, an alternative paradigm for the development of data technologies. We really need to start looking at how to address and how to achieve the same type of results from a much more modular, component-based, distributed approach. It was only when we really got to the ability to modularize and objectify our programming languages that computing really took the steps and the capabilities that we have now. So we really have to look at that again from the perspective how to do the same with smaller components, with a more networked and distributed approach. So in a sense, what we are doing is expecting development on the technology that I don't think that at the end of the day is necessarily sustainable. And at the same time, we need to look from the perspective of what are the incentives that make all of us, which, like Phoebe says, we need everybody involved and all at many different levels. What are the incentives that really will make that happen? And that I'm not really sure that those are the incentives that we have defined necessarily on the Sustainable Development Goals.
Okay, we hold on to that. In reply to this, but also in general, Andrew, Virginia says technology is going in the wrong direction, or in any way in an incomplete direction. We need new technology. I've heard presentations by companies that say we can bring down the cost of AI, and this is focusing on AI, by 3 to 6 orders of magnitude by getting, the different physics, and not just quantum also, but also elsewhere, different algorithms, of course, and the energy, where it's coming from. What you presented is let's manage what we have in a much better way, and not be in the 50s and the 70s. Do you see other sciences, natural sciences, physical sciences, coming in together and changing our energy consumption, or the way we treat technology to achieve what Virginia says?
Great question. I think the answer is, computing has been a 70-year exercise in the rebound effect, right? In Jevons paradox rebound. And what we see is massive increase in power consumption. So while I would love to have advances, I don't foresee energy use by computing decreasing. We seem to have an unlimited ability to consume computing, and I expect it's the same for AI. We have practically an unlimited capability to consume AI. So my great hope, and I applaud, the efforts to engage the broad population around the world in the cause of sustainability and managing climate change. But my goal for the last few years has been to try and harness the massive economic engine that is the investment around this large-scale computing. In the US, we feel very extremely that these large organizations have the bulk of the resources available, separate from the governments, right, to drive these kinds of changes. So I think that because they are, garnering a lion's share of the profits, right, these economic forces can be used to drive them to also make, scalable investments in the energy transition, which we've been crying out for a decade or more.
Thank you.
If I could just say one point
yes.
with regard to what Andy said, was that I think we need to have more innovative use of the additional power being used in computing. For example, the heat being generated by the data centers could be used in Chicago because they were having snow a few days back. So in that way, we should actually embrace computing and say that there's no way that we can reduce the amount of computing, but reduce the rate of growth of computing power, and also have more innovative uses of the, in a sense, the downstream effects of all this computing.
Yes, and Yanis, if you allow me, let me just reiterate how important computing is for our climate systems modeling, from where all our policy recommendations for implementation and scaling come from. All these climate models simulate the interactions of the atmosphere, oceans, land, ice, biosphere, and human systems. So we have nonlinear differential equations, millions to billions of grid cells, long time scale, large ensemble runs for uncertainty analysis, and all the global climate change models we use in the IPCC report, the Earth system models we use, the regional climate models, the integrated assessment models that bring the natural models, the techno-engineering models, and the socioeconomic models together, need a lot of computing. And not just need a lot of computing, but also AI can help transform this modeling, improving the resolution, speeding up simulations. So it's crucially important that we collaborate in this and find the most efficient way to allow increased computing, but efficient use of energy, and including all sources of energy, identifying a circular model for the production and consumption of this energy, so that at the end of the day, together, we can enable climate science to move from the descriptive to predictive to prescriptive, and at the end of the day, achieve the handling of this existential problem that we call climate change.
But I fully agree with you that we need the models. I don't agree that we need the models to be developed and designed in the way that we are doing it now. We are still very much hung up on the idea that we measure efficiency of computing by the quality of the results. We are not sufficiently measuring the cost of those results. And if we don't move to a different type of measure of computing efficiency, in which we put together the quality of the results with the cost of those results, we keep going into circles like we have been in the last few decades. So we really need to move, and we can, and there are efforts also from other disciplines, like you say, Yanis, from physics and so on, in which we can start looking at other ways to measure what we do, and by measuring things in a different way, we will also identify the ways in which we can have the same results that you need for me, and I fully agree with that, but then developed in ways that are not as costly as they are now. And there is, I think, where we need
and it's not only physics that is working on this.
It's not only physics. No, it's not only physics. I was just giving the example of physics.
Yes, I agree with what you said. We develop matrices that try to make explicit the carbon and water and other footprints of this computing. And of course, it's a huge effort to make that efficient enough with regards to their footprint on natural resources, as well as their input in the modeling exercises and the recommendations. I agree with that.
Can I make a prediction, Yanis?
Yes, please, Andrew.
My prediction is that the amount of computing and the energy consumed by computing on the planet will continue to grow rapidly for the next several decades. So I don't believe actually that a fundamental technological advance or any attempt to remetric and constrain our use can significantly slow that growth.
Let me ask you one thing, and maybe with this, it can be the end because we're 5 minutes over time, and I apologize to the organizers. The history of humanity shows that growth is intimately related to energy consumption. So as humanity and as the developing world becomes more developed, and the developed world continues to develop, we'll need more energy. But could this energy be, or these needs be satisfied with energy that is sustainable? Could we satisfy the energy, the needs that we have with smarter use of energy or with higher advanced technologies on energy, so that it's not a linear consumption, it's not a linear growth of the energy needs with the actual development of the world? That's a question for me that science, hopefully, I was born an optimist, can help us solve. But I like your prediction. So one last word, like one word or maybe two, not more. Jayant.
Game theory is the answer.
Game theory is the answer. Okay, Virginia.
You're muted, Virginia.
One or two words.
Oh, sorry. Systemic approach and inclusion is the answer.
Great. Andrew.
I learned from my economist colleagues that harnessing the animal spirits and the drive for profit is the most powerful way to change the world. So let's harness it for energy transition.
Phoebe.
And energy
Two words.
derives from many different sources. Our modeling showcases that it is possible to reach by not 2030, but 2050, climate neutrality, and at the same time, efficient energy consumption through both energy supply management in terms of the allocation of the sources from which you get energy, and energy demand management that is a big, serious issue. And I hope we can discuss this in another panel.
And I hope so too. And I hold from what you said. I mean, great. But I wanted to ask this, but we don't have time. It's not 2030 strictly. We seem to have a runway until 2050 by the UN. Thank you all very much. This was a great exchange. 1 hour was not enough by any means, but we will be connected, and hopefully we'll have another panel very soon in COP31 or before in another context. Thank you all so much. Thank you to the organizers for setting this up. I guess we are just signing off now, right?
Yeah, thanks, Yanis.
Thank you very much.
Thank you all.
Thank you.
So nice to
Thank
meet you all.
Bye-bye.
Thank you.
Nice.
Bye-bye.
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 Bye-bye.